Let's start talking about logistic regression. In this video, I'd like to show you the hypothesis representation. That is, what is the function we're going to use to represent our hypothesis when we have a classification problem. Earlier, we said that we would like our classifier to output values that are between 0 and 1. So we'd like to come up with a hypothesis that satisfies this property, that its predictions are maybe between 0 and 1. When we were using linear regression, this was the form of a hypothesis where h of x is theta transpose x. For logistic regression, I'm going to modify this a little bit and make the hypothesis g of theta transpose x, where I'm going to define the function g as follows. G of z, if z is a real number, is equal to 1 over 1 plus e to the negative z. This is called the sigmoid function or the logistic function, and the term logistic function, that's what gives rise to the name logistic regression. And by the way, the terms sigmoid function and logistic function are basically synonyms and mean the same thing. So the two terms are basically interchangeable, and either term can be used to refer to this function g. And if we take these two equations and put them together, then here's just an alternative way of writing out the form of my hypothesis. I'm saying that h of x is 1 over 1 plus e to the negative theta transpose x. And all I've done is I've taken this variable z here is a real number, and plugged in theta transpose x. So I end up with, theta transpose x in place of z there. Lastly, let me show you what the sigmoid function looks like. I'm going to plot it on this figure here. The sigmoid function, g of z, also called the logistic function, it looks like this. It starts off near 0, and then it rises until it crosses 0.5 at the origin, and then it flattens out again like so. So that's what the sigmoid function looks like. And you notice that the sigmoid function, well, it asymptotes at 1, and it asymptotes at 0 as z, I guess the horizontal axis is z. As z goes to minus infinity, g of z approaches 0. And as g of z approaches infinity, g of z approaches 1. And so because g of z outputs values that are between 0 and 1, we also have that h of x must be between 0 and 1. Finally, given this hypothesis representation, what we need to do, as before, is fit the parameters theta to our data. So given a training set, we need to pick a value for the parameters theta, and this hypothesis will then let us make predictions. We'll talk about a learning algorithm later for fitting the parameters theta. But first, let's talk a bit about the interpretation of this model. Here's how I'm going to interpret the output of my hypothesis h of x. When my hypothesis outputs some number, I am going to treat that number as the estimated probability that y is equal to 1 on a new input example x. Here's what I mean. Here's an example. Let's say we're using the tumor classification example. So we may have a feature vector x, which is this x0 equals 1 as always, and then our one feature is the size of the tumor. Suppose I have a patient come in and they have some tumor size, and I feed their feature vector x into my hypothesis, and suppose my hypothesis outputs the number 0.7. I'm going to interpret my hypothesis as follows. I'm going to say that this hypothesis is telling me that for a patient with features x, the probability that y equals 1 is 0.7. In other words, I'm going to tell my patient that their tumor, sadly, has a 70% chance or a 0.7 chance of being malignant. To write this out slightly more formally, or to write this out in math, I'm going to interpret my hypothesis output as p of y equals 1 given x parameterized by theta. So for those of you that are familiar with probability, this equation may make sense. If you're a little less familiar with probability, here's how I read this expression. This is the probability that y is equal to 1 given x, so given that my patient has features X, or given my patient has a particular tumor size represented by my features X, and this probability is parameterized by theta. So I'm basically going to count on my hypothesis to give me estimates of the probability that y is equal to 1. Now, since this is a classification task, we know that y must be either 0 or 1, right? Those are the only two values that y could possibly take on, either in the training set or for new patients that may walk into my office or into the doctor's office in the future. So given h of x, we can therefore compute the probability that y is equal to 0 as well. Concretely, because y must be either 0 or 1, we know that the probability of y equals 0 plus the probability of y equals 1 must add up to 1. This first equation looks a little bit more complicated, but it's basically saying that probability of y equals 0 for a particular patient with features x, and given our parameters theta, plus the probability of y equals 1 for that same patient with features x, and given our parameters theta, must add up to 1. If this equation looks a little bit complicated, feel free to mentally imagine it without that x and theta. And this is just saying that the probability of y equals 0 plus the probability of y equals 1 must be equal to 1. And we know this to be true because y has to be either 0 or 1. And so the chance of y being equal to 0 plus the chance that y is 1, those two must add up to 1. And so if you just take this term and move it to the right-hand side, then you end up with this equation. It says probability of y equals 0 is 1 minus probability of y equals 1. And thus, if our hypothesis, if h of x gives us that term, you can therefore quite simply compute the probability, or compute the estimated probability, that y is equal to 0 as well. So you now know what the hypothesis representation is for logistic regression. And we've seen what the mathematical formula is defining the hypothesis for logistic regression. In the next video, I'd like to try to give you better intuition about what the hypothesis function looks like. And I want to tell you about something called the decision boundary, and we'll look at some visualizations together to try to get a better sense of what this hypothesis function of logistic regression really looks like.